All right, guys, welcome back. So we're continuing on with rational functions, and what we've seen so far is an example of f of x, which is 1 over x, which is our parent function, and then we've also seen transformations on it, which would be something like g of x, which is 3 over x plus 2 minus 1. But what happens if we have something a little bit more complicated? So what about, for example, h of x, which is x plus 4 over x minus 2, or r of x, which is even more complicated, which is x squared plus 5x plus 6 all over x plus 2. Okay, these are what we really call rational functions. And so a rational function has this form. We have f of x is a rational function. If it's g of x over h of x, where g of x and h of x are each individual polynomials. And I know that kind of looks sounds confusing, but really just look at r of x over here, right? And we'll see that it's basically just a polynomial over a polynomial. Okay, now we can say polynomial over polynomial, and even if we look at our parent function, which is 1 over x, technically they're polynomials. They're just really, monomials. One has a degree of 0 and one has a degree of 1. Okay, so realistically it extends to all those types of situations. So in order for us to have f of x in its simplest form, all right, we have to have g of x and h of x have no common factors, and that'll come into play just a little bit. Okay, so what we're really going to be focusing on today is called the discontinuity of rational functions. So a function, right, f of x, is said to be discontinuous if there are essentially interruptions in the graph. More specifically, if there's a value of x such that h of x, the denominator, will equal 0, then the function will be discontinuous at a point. And we've seen examples of this, right? If I pull up Desmos here, right, if we go 1 over x plus 2, we can notice that we have an interruption essentially in the graph at negative 2. Okay, so we have our asymptote over here at x equals negative 2. So that would technically be a point of discontinuity. So for example, how do we tell these algebraically? For example, h of x on this first one, right, we know that since if x minus 2 equals 0, right, this function will essentially blow up. It'll have a point of discontinuity. So at x is equal to 2, right, we are h of x is said to be discontinuous. Right. Looking over at r of x, all right, same kind of idea. So if we know that x plus 2 is equal to 0, right, then at x equals negative 2, right, r of x is discontinuous. Okay. So, and again, there's two different types of ways that we can kind of look at discontinuous. And also what we want to kind of notice is that, hey, you know what? What happens if our numerator becomes 0? Right? If our numerator becomes 0, we're actually going to find that we have some x-intercepts. Now, we're not going to go into it, but just some food for thought for later. Okay. So let's try simplifying, though, and see kind of what that does and what happens here. Okay, so if I look at h of x, right, we see that it's already simplified. But if I look at r of x, right, I can actually factor the numerator. Okay, and if I factor this numerator, I should get x plus 2 times x plus 3. And then it would be all over x plus 2. All right, but one of the things that we want to notice while we're doing this is, hey, they both have an x plus 2 in the top and bottom, right? So why can't I factor that out? And so this actually becomes x plus 3. But that's kind of weird, right? Because we just said, all right, that at r of x, that it's discontinuous at x equals negative 2. But if we simplify it out and we get x plus 3, what happens? Are we still? Right, so the question is can x equals, that should be negative 2. Sorry, I'm going to change that. I'll delete that, but I'm going to change this. All right, sorry, just for future reference. Done. Okay, so the question is can x equal negative 2 work now? All right, the answer is no. Right? So, and there would be a reason why, because we really have two types of discontinuity. Right? And that x plus 2 is an example of our first type of discontinuity, which is called a removable discontinuity. Another word for removable discontinuity, right, is what we call a hole in the graph. So what a hole is for if we have our polynomial, if there's a hole, right, what they're saying is that there's a hole at x equals a if x minus a can be factored out of both the numerator and denominator. All right, so here we have another example, x squared minus 2x over x squared minus 4. Right, if I factor the top and bottom, I get x times x minus 2 over x plus 2 times x minus 2. Okay, so if I factor, what we notice is that if I factor this out, right, that means that we have a hole at x equals 2. Okay, and the reason why is because, again, that would make this either these are both kind of getting removed, and essentially we would have in the denominator, we have positive 2 and negative 2 should be essentially asymptotes or points of discontinuity, right? But because I can remove it, right, we actually have a hole at x equals 2. Okay, but what about the x plus 2? What's going to happen there? So because we can say right here, right, that f of x is discontinuous at both x equals 2 and x equals negative 2. So it has 2 points of discontinuity, but we notice that there's a hole at x equals 2. Well, what happened to the other one, right? And so just to kind of look at a hole, for example, right, we're going to go over here to our x squared plus 5x plus 6. All right, remember when we simplified this, I'm going to turn that off. When we simplified this down, so even though that doesn't look like it has any asymptotes or anything like that, right? When we simplified it down, we got we made it look like x plus 3, right? So how are these two different? Well, if I look at x plus 3 and I go over here to negative 2, for example, I just kind of hold negative 2. I have a value of 1, right? So I can actually evaluate this guy. But if I look at this function and I go to negative 2, and I try to find points of it, and I go over here to negative 2, well, it's undefined. And you can see, right, if I'm looking at this graph, you can see how it all of a sudden there's a little white hole dot that appears, and we actually have a hole in our graph. It's basically a little jump. So that's kind of the difference between when we simplify it and when we don't, and that's an example of a hole or a removable discontinuity. Okay. So that's what's going to happen to this graph is we're going to have a hole at x equals 2, but what's going to happen at x equals negative 2? Okay, so that leads us to our second type of discontinuity, which is called a non-removable discontinuity, right? Or in other words, asymptotes, right? Now there's two types of asymptotes that we've looked at so far because we've seen examples of these before. We have vertical and horizontal asymptotes. We're going to save vertical for later, right? And we're just going to, or sorry, horizontal for later, and we're just going to look at vertical asymptotes. Okay, we know there's vertical asymptotes at all zeros of h of x, the denominator, if the zeros cannot be factored out or removed from both the numerator and denominator. So in this example above, right, we see that we couldn't remove this x equals negative 2, so we actually had a vertical asymptote at x equals negative 2. Okay, so and we're going to look at three kind of examples. If we look at number 1, right, we can see that x over x plus 2, right, has no we can't factor anything out, so we know that there is a vertical asymptote at x equals negative 2, right? Because again, if x plus 2 is equal to 0, right, then that means that x equals negative 2 is we have a vertical asymptote, okay? So for number 2, right, because we can see that we have an x minus 2 gets kind of factored out, right, we can get that this is going to be, we have a hole, sorry, I'm going to use green for that. We have a hole at x equals 2, but we have a vertical asymptote, since x plus 3 can't be removed, at x equals negative 3, okay? Likewise, but number 3 is going to be a little bit different, right? Number 3 is kind of weird because if I simplify this guy, right, this is the same thing as x minus 1 over x minus 1 times x minus 1, and we'll see that, hey, wait, right, I can remove this, so we should have a hole at x is equal to positive 1, but right, this one can't be removed, so we actually also have a vertical asymptote at x equals positive 1. Right? And the truth is if we have both a vertical asymptote and a hole at the same value, right, that vertical asymptote is going to essentially win every single time. Right? Because a vertical asymptote, my function can't ever equal it anyway, so of course there's going to be a hole because there's really it's never going to be anything there. Okay? And so that's kind of how we can determine between vertical asymptotes and horizontal asymptotes. Now I'm going to look at some examples in the next video just to kind of help you out a little bit more and so you can see some examples before you actually work on your assignment today.